Thank you, Dan, and thank you to all the organizers of the program and the organizers of the conference. I'm very excited to be here. All right, so these announcements are going to stay on the board, so in case you forget, you can keep reading them. Maybe they will stay even for the afternoon, or one will be erased at a time. All right, so well, I'm very excited to talk about this right now because both of my co-authors, Gabe Angelini Noel and Maximilian Peru, are here in the audience. So feel free to correct my mistakes. So the goal of the talk and of this project is to generalize some well-beloved constructions that many people here have thought about. So one is THH of a ring or a ring spectrum. So the input here is a ring. And we know this carries an S1 action. And then there's also this real topological Hochschild homology called THR, which maybe some people here have thought about a lot. So the input to this is a ring with involution. And this gadget carries an O2 action. And what we want is to kind of simultaneously generalize both of these. So we're going to have a more general construction that we'll call PHG. So this is what we'll call topological homology, where the input is going to be a ring with, for now I'll put it in quotation marks because I haven't defined it yet, so twisted group action. But let me say for now, so this will be a generalization of involution and G action. And this is going to have an action of a topological group that I will also describe how it comes about. But so what we're interested in is a particular example that comes out of this. So the example that we're interested in, that we want to create, is going to be a quaternionic version of THH. So something that we'll call THQ. So maybe we'll call this quaternionic. So if this was real THH, we'll call this quaternionic THH. And the input here, so the R, is going to be a ring with twisted C4 action, which is also Q4. And the action, so the topological group acting on this is this group PIN2, which shows up a lot in low-dimensional topology these days. So this group, so it's a subgroup of the unit quaternions. So you can think of it as two copies of S1. So S1 union J, S1 inside the quaternions. Okay, so that's the goal. So we want to construct this example that carries a PIN2 action, and it's going to fit in this slightly more general framework that also generalizes these simultaneously. Okay, so let's maybe start with a very basic question about THH, which is how do we get the S1 action on THH? Okay, and so let's maybe remember here that THH of a ring is the realization of the cyclic bar construction. Where we take into account these actions at each level of the cyclic groups. So this is the cyclic bar construction. Okay, so first, let's note something very simple, which is if we had a topological group, so if G dot is, sorry, not a simplicial group. So if we had a simplicial group, and if this was acting on some simplicial object, X dot, then we would get an action of the realization of G dot on the realization of X dot. And also, let's just note that, so if we look at the simplicial circle, so S1n, at level n, this is isomorphic to Cn plus 1, just as a set. Okay, but of course, the simplicial circle is not actually a simplicial group. So we're not in this, nice context where we really have the action of a simplicial group acting on a simplicial gadget. So we don't get the action, quite like that. But so this was the insight of Fyodorovich and Lodey. It turns out that you don't actually need a simplicial group acting on your simplicial object to get an action of the realization. But it's enough to have this weaker structure called a cross-simplicial group. And that's exactly what the simplicial circle is. So let me introduce this notion now. Right, so maybe, right, so the upshot here is that actually you can get away with something weaker. So let's maybe also note, so the cyclic category, if we think about it, so if I were to draw it, it has objects, the natural numbers, so 1, 2, and so we have all of our maps that come from delta. But in addition to this, we also, so what we have added is exactly the automorphism. So delta does not have any non-trivial automorphisms. And the way you get the cyclic category is precisely by baking in the automorphisms of every n to be the cyclic groups. So the cyclic category is nothing but delta plus automorphisms plus some compatibility. Okay, so here is the more general definition due to Fyodorovich and Lodey, and independently also Krasserhaus. So the gadget is called a cross-simplicial group. And we're going to use this notation delta G. And what it is a category with, so the objects are going to be, again, the natural numbers. So n for every n bigger than or equal to 0. It's going to, so delta is going to sit as a subcategory in here. But now we're also adding in automorphisms. So we're going to have automorphisms in delta G of n are going to be some group G sub n. And the other condition is, so the compatibility is going to say that for every morphism, so if I can, so for every morphism in delta G, there exists a decomposition as a morphism in Gn followed as a morphism by a morphism in delta. So in other words, so let me draw this as a little diagram. So if we have something m to n to n, so this is something in delta, and this is something in Gn. What I'm saying is that I can complete this. So I'm going to have some induced map m to m, which is going to live in Gm. and I'm going to get some map M to N, which is also in delta. So let's call this G star delta. Okay, so some notes about this. So we get these operations. So phi star, right, so this makes the sequence of groups Gn, in particular, it makes it into a simplicial set. Then, moreover, if we look at this operation G star for any fixed little g, this gives an action of Gn on the set of maps from N to M. So this gives, well, maybe I shouldn't call it an action. Maybe I'll put this in. So on, so an action of Gn on the set of maps in delta from N to M, but it's not quite an action, so this is where the twisting comes in. So this preserving multiplication with a crossing. So therefore the name cross-simplicial group. So let me just give you an example. So now there's a bunch of axioms that you can write. There's maybe 7 of them, and they have subparts and so on. But just to give you a taste, right, so for example, if I do phi star of GH, right, so this is not going to have the homomorphism property, but it's something that looks a little bit like a cross homomorphism. So this is going to be phi star G, G star phi star H. And similarly, if I do G star of phi psi, this is going to be G star phi composed with phi star G star psi. So we get these kind of crossings.
So all these properties are part of the definition?
Yes, these are all part of the definition. So you can axiomatize, but now I will give you an equivalent definition. So equivalently, we could define a cross-simplicial group. So cross-simplicial group is, so I could just start with a simplicial set Gn, where each Gn is a group, but this is not a simplicial group. Right, so again, keep in mind the example of the simplicial circle. So we have all the Cn's, but it's not a simplicial group. And now impose some conditions. So with all the Gn groups together, and now we're going to impose some conditions. So together with group homomorphisms from Gn into sigma n plus 1. Right, so this is the automorphism of the set of n elements. So such that, so now if I look at di of gh, this is going to be di of g, and again we're going to have this twisting, so this is going to be dg inverse I of h. And similarly, Si of GH is going to be SIG SG inverse I H. Okay, so now I'm slightly abusing notation when I'm writing, so when I'm writing an element applied to an I, right, I'm implicitly using this homomorphism. Okay, so such that, so we're not done, such that the set diagrams also commute the following diagrams. So if I do n minus 1, so if I take delta I and the delta G inverse I and the G and now di of G, well, plus a similar one for the degeneracies. Okay, so sigma I, sigma G inverse I, G, and SI G. Okay, so now these are actual set diagrams, and we're asking for these to commute. So this data I'm saying is equivalent to that data, and you can translate back and forth. Okay, so the first thing to note is that given a cross-simplicial group, right, so you can think about it either way, and we think about it, you know, depending on what we want to do, you can use either perspective. So the thing to note is now that we can define, so this is not a simplicial group, but we can still define an action of a cross-simplicial group now it's probably convenient to think about it like this, as a simplicial set where all the GNs are groups and that satisfy these extra relations. So G dot acting on a simplicial object. So level-wise, we're going to have group actions. So Gn acts on Xn such that, and now we're going to impose some of these relations. So di Gx is di G, dg inverse I x. And okay, another one for degeneracies. And this is exactly the data. So I'm just translating the data of what it means to have a functor from delta G up into some category C. Maybe set or top for now. And we'll want it to be spectra later. Okay, so now the big theorem. So maybe like using Magdalena's talking points, the first magic point in the talk. So it's this theorem of Fyodorovich and Lode, where, so they show that if you have a cross-simplicial group, so if Gn is a cross-simplicial group, the realization of G dot, so this is a simplicial set, if you take its geometric realization, this is actually a topological group. And if you have thought about, you know, the simplicial, well, you've probably thought about the simplicial circle, right? And if you have thought about the action of S1 on THH, this might also look familiar. So if G dot acts on X dot, then we get an action of this topological group on X dot. But this fits into this slightly more general framework, so it applies to any cross-simplicial group. Okay, so some examples. So far, okay, many definitions and combinatorics. So let's give some examples. Okay, so many examples of cross-simplicial groups. Okay, so let's start with the obvious examples. Right, so if I just take delta, of course, there's going to be a cross-simplicial group. Right, so here, the Gn are all identity. Another example, right, and now I might think in either description. Okay, another example, another one of the obvious examples that are not new in any way is any simplicial group. So if I have a simplicial group, then I can just think about these actions being trivial. And so that's another example of a cross-simplicial group. Okay, so now some more interesting examples that don't fit into these classical framework. So I guess this is still pretty classical. So cons lambda, the cyclic category. So this is a prototypical example. So here, as we saw, Gn is C n plus 1. Right, so this is the simplicial circle. And we have these inclusion maps into sigma n plus 1, and those are the maps. And we already know the realization of this is S1. So that's the topological group that we get in that case. Okay, so another example that will be important is the symmetric, sorry, let me do next the dihedral. Right, so this was the cyclic category. So next we have the dihedral category. So here Gn is going to be a dihedral group, D2 n times n plus 1. And the realization of this is going to be O2. So next we have, oh, I should probably say, okay, let me do the quaternionic case, right? So that's the one that we're after. So quaternionic category. So this is going to have Gn are going to be these generalized quaternion groups. And the realization of this is pin 2. So this interesting topological group. Right, so this was two copies of the circle that are flipped. So these are two copies of the circle that have a C4 action. And right, and here G naught, you can notice, so if n is equal to 0, C4 is going to be our first group there. Okay, so now some other examples that are also going to be very important are the symmetric category. So here the GNs are just the symmetric groups. And the realization of this is actually contractible, but nevertheless, this is going to be a very important example, as you will see. And the hyperoctahedral category, where the GNs are now these Rees products, C2 Rees sigma n plus 1. And the realization of this is also contractible. Okay, there's also, the braid groups also form an example. Okay, but maybe that's not going to be so relevant for our discussion today.
What's the realization?
I think that's also contractible, right? Yeah, but these two we will see will be very important in our constructions today to even get to this pin 2 equivariant version. Okay, so maybe one remark that I want to say here is that actually, so the reason why this is very important is, so for any cross-simplicial group, there exists a map from delta G to delta H. And that's important. Okay, so now let me indicate, right, so in order to show, so I just claimed that all of these are examples, right, but of course for each one of them there's a bit to check. As we saw, there's a bunch of combinatorial relations that go into defining a cross-simplicial group. And you might be familiar, with the cyclic example, but for each one, right, you'd have to check. So since these are going to be very important in our constructions, let me give you some idea of why these two are cross-simplicial groups. So we have the first definition, right? We need to give recipes for defining these operations phi star and G star. Okay, so let's look, and this can be done via pictures. So I'm just gonna, so it's my chance to draw a picture in the talk and use some colors. Okay, so let's look at these two examples, and I'm just gonna tell you, the kind of the recipe that goes into how you define the operations, and then of course, you know, there's lots of things to check. As I said, there's like about 7 axioms or so that you'd have to check. Okay, so how do we make sigma, delta sigma into a cross-influential group? Okay, so here I gave you an example of a phi and a g, and I need to tell you, right, I need to tell you how to define the g star phi and the phi star g. Okay, so let's see what we can do. Okay, so there's not much choice at the top for the mapping in delta, because so that's completely determined by the sizes of the pre-images, and it has to be order preserving, right? So this is why I'm using the colors and going through this example, where I'm just going to follow through. So this has one pre-image, and it needs to be the first one in the order. This one has no pre-image, so I'm going to skip it. Then the green, right, so this has 3 pre-images. And lastly, 3 has 2 pre-images. Right, so I'm just preserving the order. Okay, so, and now the way we define the permutation phi star of g is I'm just going to connect the strands. Right, so that's the recipe. I just connect the strands. So I'm going to following orders, and this is important. So, okay, here there's nothing to follow. So here I'm going to connect the first red to the first thread, and then I'm going to connect the first green to the first green, second green, third green. And that's the recipe. So I define for your permutation, right, it depends on phi and g. And now the claim is that if you were to check, you know, all the relations, that this satisfies it, this recipe. Okay, so now let's think about the hyperoctahedral group. Right, so here we have a permutation, but not just that. So an element in this group now is a permutation plus a tuple of elements in C2. Then I'm gonna use the notation plus and minus for the elements of C2. Right, so I just label the strands by either plus or minus. Okay, so let's start. So here first at the top, it's gonna be exactly the same, because this needs to be a mapping delta. So I'm just gonna preserve the orders. Right, so this is the same map phi. Okay, but now I need to give you a permutation and then also a tuple of elements in C2. So now the permutation is going to be different. It will matter what those parities are. So I'm going to look at each one of these, if it's a plus or a minus. And if it's a plus, right, so we see the red. So let's start with the yellow. The yellow is only one thing. So I'm just going to connect the color. The red is a plus, so I'm going to connect the color, preserving the order. And the green is a minus, so I'm going to connect the strands, again the colors, but now I'm going to flip the order. So I'm going to connect the first one to the last one. Okay, I'm just flipping the order. And that's the recipe. Right, so again, the claim now is that, of course, there's lots of things to check, right? So now you have to write some pages of checking a bunch of combinatorial relations, but the claim is that this recipe gives a cross-influential group structure where the levels are these product groups. Okay, so I will leave this picture here. It's lots of colors.
I just read it so pretty.
I heard. Thank you for saying it louder. Okay, so I still haven't defined what the, well, let's get to, first let me make a definition of a group with parity. So a group with parity is a homomorphism. So it's a group G that comes with a homomorphism with C2. Right, so we can talk about even and odd elements in G. And small remark is that for any cross-simplicial group, so from the definition of a cross-simplicial group, we can get a canonical, so from the definition, we can extract a parity G naught. Well, as I said, it has a map. So it's this more general fact that you actually have a map of cross-simplicial groups from delta G to delta H, and H naught is just C2. And you can be very explicit about what this is, but let me skip that so we can get to maybe a first technical result that we show. Okay, so I'm going to tell you in the course of the talks, there's going to be 3 technical propositions, and then we will assemble into the construction that we want. So the first of them is the following. So if we have G, a group with parity, there exists a cross-simplicial group. So this will be a generalization of the hyperoctahedral cross-simplicial group. So we're saying there exists a cross-simplicial group that we'll call delta. I'm also having trouble, like Morgan, with the letters. Maybe this is a rho or a phi. Yeah. Okay, so rho or phi. Right, let's call it phi. With sigma, where the GNs are going to be, so instead of C2, we're going to have G res sigma n plus 1. And for any delta G, there exists a factorization delta G. So we already know we have this map to delta H, but our claim is that this factors through delta naught, well, delta lambda naught res sigma. So the cross-simplicial group that arises from this canonical parity on G naught. So maybe a quick remark here. So 2 particular examples of this are, so if G is the identity, then this construction that we're making is just delta sigma. So it's the one that we defined over here via this picture. And if if the group with parity is the identity on C2, then this construction just recovers delta H, so the hyperoctahedral one, the one that we defined over here via this picture. And otherwise, it's just a generalization of this, where instead of these labels, we have elements of G, but they each map to some element of C2, and we just have to keep track of that extra data. Okay, but maybe because, so that we don't, so we have our first, technical result, this construction that generalizes delta H, so that we don't lose track of our goal. So let me get back and restate our goal. Right, so our goal was to generalize the cyclic bar construction. And so recall THH of A. So we're going to use the Nicola-Schulze description. Yes, Thomas is nodding. So this is what we want. This is what we want to generalize, right? So we have a map from delta op into lambda op, and this. So it's a crucial fact that there's an isomorphism here with lambda, and then what Thomas and Peter do, right? So this has a map into a Soch tensor, the active part of the associativity operator, the category of operators, Soch tensor active part, and spectra. So if you have a ring spectrum, it's exactly the data of a map from here. And I'm going to come back to this because we'll want to really analyzed each one of these pieces, right? So for now, if you're not familiar with all of the ingredients here, I will come back to all of these, right? So here, assoc is the associativity operand.
Is R A?
Yes. So let's maybe make this R. Thank you. Right, so assoc n is sigma n. Okay, so far we have only, so we want to generalize, all the pieces of this construction. So far I have only, told you a little bit about delta, and that delta has these generalizations, right? But ultimately, right, we already, you can suspect, right, like this first result was that every delta G has a map to something, right? So the goal will be to relate, that something with something in terms of operands, and then ultimately, okay, so, but now maybe, okay, so far we've attacked a little this end of the construction, so let's maybe attack this now from the other end, right? So the other end is, what was the input here? It was a ring, right, which was exactly the data of one of these maps. So let's maybe even ask, so what input do we want now? So we haven't even quite established that, right? So what input do we want for our construction THG? So let me maybe go. Okay, so what input do we want? So now let me finally define this. Well, so we want to define now what a ring with twisted G action actually means. So given a group with parity, so G to C2, I think we call this phi. So a ring with twisted G action is going to be, is a ring R with actions. So G is going to act as a homomorphism if G has parity 1. So this is if phi of G is equal to 1. And G is going to act by an anti-homomorphism, so map from R up to R if the parity of G is minus 1. So as you can see, this recovers some well-known examples. So if phi is trivial, this is just a ring with G action. And if phi is the identity on C2, this is a ring with anti-involution. Okay, so more generally, we can talk about, so we have the notion of a category with parity. So this is just a map from a category to BC2. And given a category with a C2 action and a group with parity, we can define the notion of a twisted G object in C. So this is just going to be a functor from BG to the Gruden deconstruction, so C2 semi-direct product C that lives over BC2. And so now lastly, so if C is any co-complete symmetric monoidal infinity category, then an algebra with twisted G action. So it's just going to be a twisted G object in this sense. So is a twisted G object in algebras in C, where the C2 action on this comes from sending M to M up. So you send a monoid to M up. Okay, so see time is running out quickly. Okay, so let's get now towards operads. So we want to, so the goal is we want to interpret these as algebras over some operad, just like rings were algebras over a the associativity operad. So a definition from a really cool paper of Salvatore and Wall. So they define an, so if if O is an operad in G spaces, they define a twisted G operad so O semi-direct product G. So at level n, this is going to be On times n copies of G. And do I want to tell you the operad map? Maybe not. So is it okay if I spare you the definition of the operad map? Right, so the operad map, right, is going to be some long thing because we have all these tuples, right? But the operad map will use the operad map of O, right? But now also combine, like all the G actions. So I guess I can refer you to their paper. It would probably not be so enlightening. Or you can try to write as an exercise some guesses for what the operad map should be. But let me just give you the examples. So we're really trying to define this operad by hand, but there's many kind of wrong choices that you can make. And then, we found that this is actually an instance of their definition in their paper, which is awesome. So if you take a group with parity, then I'm going to make a definition of assoc phi to be, so it's going to be a particular case of their construction, assoc semi-direct product G. And so so G acts on assoc by the action of, so the map from G to C2, and C2 acts on assoc by reversing orders. Okay, so with those definitions, so we make this definition with these specifications, and now sort of the second technical result that we will need is that a ring with twisted G action, in the sense that I defined, is exactly an algebra over this operad assoc phi. Okay, so great. Okay, so we're so now we have made sense of the input that we want in the construction from the other end. And lastly, we want to relate, right? So now we want to actually relate this to cross-implicial groups. Okay, so recall, right, that if O is an operad, we have this category of operators, O tensor, whose objects are the natural numbers, and the morphisms between M and N are going to be maps of finite pointed sets from M to N plus choices of, so a tuple of points in the operad. So O, where I look at the size of the inverse images and pick a point in the operad in that level. right? So this was the gadget that, you know, May Thomason had the insight. This mediates between Siegel's gamma spaces and operads. Okay, so the example that we care about, so is assoc, but also these assoc phi's. So, for example, assoc tensor, right? The objects are the natural numbers, and the morphisms from n to m is going to be some map of finite points in sets plus orders on the preimages. Okay, so what I didn't tell you is what the composition rule is. Okay, so no chance I'm going to tell you that, so that's right a bit tedious, right? So plus you have to make a composition rule, and that will, of course, right, be defined in terms again of the operad structure map, but also you have to keep track, right, of doing the right orders at the right time. So yeah, so that can be a bit tedious, but now let me maybe get a chance to use colors again, and we still have, okay, so we still have the picture, but I think you know what, well, sorry, you don't need the picture. We know what the maps are in delta sigma, right? So everything can be factored as a map in delta plus a permutation. So we want to relate this, right, to operads. So let's think about just the case of the symmetric case, right? That's the simplest case that we're trying to generalize. So let me maybe make a little note here. So let me just do one example. Okay, so of course, the objects are the same. In delta sigma and in the assoc tensor, the objects match up. So let's look at the morphisms. So I'm going to draw a morphism in assoc tensor, 3, 4, 5, 6. Okay, so I'm going to pick some colors. Okay, so let's say 1 goes to 3, and 2, 4, and 5 go to 1, and maybe nothing goes to 2, and 2 things, 3 and 6 go to 4. Okay, so now it's a pretty simple exercise, right? If I told you how from this data, oh, sorry, I do need more data. So a point in this operad, like a map in this operad in O, so in the category of operators, assoc tensor, right, is this map in fin star. So know that I'm ignoring the 0. That will be important. So I'm looking at a map where maybe 0 goes to 0, nothing else goes to 0. So I also have the data of some order of the preimages, right? So here on the preimage 2, 4, 5, these are ordered as 5, 2, 4. And on the order of 3, 6, these are reversed. So suppose that I'm giving this data, right? So some data also about orders on the preimages. Okay, so now given this data, you can see that you can translate into the data 4, 5, 6. So if I wanted to create a permutation and a map in delta, okay, so the map in delta, again, there's not much that I can do because it has to be order preserving. So 3 things go to 1. If I want to factor this in some way, 1 thing goes to 3 and 2 things go to 4. But now so know that in general, I could not create this permutation here because within the preimages, right, you could permute things and you could get the same map in different ways. But if I also want to take into account this data of some given order on the preimages, that now precisely tells me how to make such a map. So I have 3 and 6 need to go to 4, but now I'm told to swap these. And 1 goes to 4. Okay, so there's only one thing there. And then in the blue, I have 2, 4, 5. So these need to go to 1, 2, 3. And again, I'm told what to do by this permutation. Okay, so what we have observed here is that a map in So this is a map in a Soch tensor, corresponds to a map in delta sigma. Okay, so this is pretty clear recipe of what to do. But what's hard is that actually the compositions also match. So that's, you know, the very painful part. So I didn't even tell you what the composition was, right? And you can also use some formulas for composition in the categories of operators. And through a very careful check, you can see, you can actually check. So this is the hard part, that the compositions actually match. Right, so it was easy to reconcile objects and morphisms. Okay, so this now leads me to okay, so maybe it would have been good to leave the goal, but you can remember it. Okay, so we're almost ready. So the third proposition and ingredient that we need is that so if we have a group with parity, and if I look at the Soch tensor, but the active part, so only those morphisms where nothing goes to 0 other than 0. So see here, I have ignored. This would go wrong, right? If I couldn't do this matching if I had things that map to 0 here. So if I look at this active part, the claim is that this is the same with this category of operators that we define in proposition 1, and we have to add an initial object to make things match up. We don't have to worry about that. So in particular, a particular case of this is what we just observed, right? So a Soch tensor act is delta sigma. Yes.
Missing the phi on the left.
I am missing
In
a
the
phi.
statement.
Yes, thank you. Thank you. So this is why it's great to have your collaborators in the audience. Yes, very important. So we definitely want the phi here, right? So this is a more general statement than this, right? For every phi, we have this more general operand and then this more general category of operators, cross-simplicial group that we constructed, and we're saying that those match up. Okay, so now we can define, finally, we can define topological homology for rings with twisted group action. But assuming, so I'm gonna make this extra assumption now that, so assume also that this is isomorphic to delta G op, that it's a cross-simplicial group with duality, as we would say. And so suppose that R is a ring with twisted G0 action for the parity, so this parity that we get from the cross-simplicial group. Okay, so now the definition, so it's exactly what I just erased, but we're going to generalize the inputs to the construction. So we're just going to follow Nicolas Schulze, and so step 1, we're going to map, instead of the cyclic category, we're going to map into delta G op. So I'm assuming that we have this duality. Okay, so now, our first technical result gave us a map into delta of this cross-simplicial group that we defined with respect to this parity. But now the third technical result that I mentioned identifies this with a Soch tensor, a Soch lambda naught active tensor. And lastly, the second result that I mentioned was that an algebra, so the ring with twisted G0 action is exactly an algebra over this. So this will give us a map to spectra. Okay, so in the remaining time, so let me tell you some full conclusions now. And well, so let's start with some examples. So in the last 5 minutes, let me just mention the examples and tell you one theorem that we can prove about this new construction. So first, let me maybe also say that what this construction does, right? So it makes precise some kind of bar construction with respect to these GNs. So what the construction does is exactly makes precise. So instead of the cyclic groups, now we have these actions. Okay, so anyway, so note, right, that we needed delta G to be the same with delta G op. And this is true for, so we already know for delta C, which is gamma, the cyclic category. It's also true for delta D. It's also true for delta Q. So it's not true for delta H and delta sigma. But since I'm running out of time, let me quickly say that those, nevertheless, you can still define the positive, what you call the positive version of those by just taking the column it's starting at this point. And when you have everything, you can relate the positive part via taking homotopy orbits. And those actually also give very interesting theories. Hyperoctahedral and symmetric homology are very interesting. So they're not at all boring. But since I only have 3 minutes left, let's get to the example that we care about the most. Right, so delta C gives THH of R. This has an S1 action. Delta D recovers THR. So this has an O2 action. And delta Q, right, so this is new. This gives our THQ. And now the ring is a twisted ring with C4 action. And this has a pin 2 action. And now in the last 2 minutes, let me maybe just tell you a theorem about THQ. Right, so what is topologist's favorite rings? Okay.
Sphere.
Okay, and more generally, okay, sphere is a good one. And more generally, loop X, right? And remember, right, recall, so we have this beautiful result about THH being the same with the loop space. So kind of, well, we would want such a theorem, right, in order for this to be meaningful. Okay, so let's maybe note, right, so, well, how do you make loop X into a ring, right? You just concatenate the loops. So now maybe think about what would happen to give you an idea of what, even in the THR case, right, why you get a ring with anti-involution. So if you were acting on the loops, if you were taking a sigma that reverses the direction of the loop, just think for yourself what would happen, because I'm running out of time and it would be easier to figure out. Right, so what happens if you concatenate and reverse loops? You'll see that the order gets swapped. So it's exactly a ring with anti-involution. And now what happens, right, if I have a C4 action on X, and I also act by C4 by, 2 elements reverse the direction of the loop, they act by anti-involution. So this is going to be the input. Okay, so THQ of, I'll call it loop sigma X, where, lambda. So lambda is the map from C4 to C2, and X is a C4 space. Right, so now it's really C4. You really need to do it 4 times to get back to the identity, because we're also acting using the C4 action on X. Okay, so in the last 40 seconds, you were right about this clock. It is very daunting, but it's good. It's good. So I'll just maybe say this, that this is a twisted. So what we get is, so this is the generator of C2. I'll call it tau. And this is a twisted loop space. So the claim is that we get a pin-2 equivariance to a twisted loop space if we plug in this C4 twisted ring. All right, so I think it's time to stop.
Questions?
Is there a good notion of Morita equivalence for TH2?
That's a great question. Probably, but we haven't thought about it. I guess have people thought about it for THR? Is it worked out? Thomas, maybe you know. It for sure should be, but we haven't thought. This is pretty new, so there's many questions.
The moment you define it in terms of the category,
Yeah,
it's
yeah.
built in, I guess, with what HR has been done.
Oh, or Morgan.
I was just going to ask how restrictive this condition that delta T is equivalent to G off, delta G off is. Like, are there examples you'd like to apply to?
No, so as I said, I didn't have time to go over these other examples. So if you don't have this, like for delta sigma or delta H, you can still define, you can still start here and define, so, and even when you have this, you can still define that and call it TG plus, right, following notation, like the positive cyclic homology and so on. So you can still define that gadget. And then when you do have the duality and have the whole thing, right, they are related via taking homotopy orbits. But you can still define that, and that is, so you can still make sense of hyperoctahedral and symmetric homology, and those are very interesting things. And we have done some calculations also, and kind of building on algebraic results that, I don't know if Daniel Graves is here, but he has done extensive work on hyperoctahedral homology. He's here in this program. Okay, maybe not here right now. but those are still very interesting theories.
Yeah, I was just wondering, I mean, does this refine to a genuine pin-2 spectrum?
Oh, great question. I mean, we hope, and hopefully this is like, so we haven't done it, but our hope is that, right, that this is probably the norm from C4, that you can,
in the commutative case.
yes. But again, like there's a lot to work out there.
But if it was genuine, it would be genuine for what? For finite subgroups of pin-2? What are those?
Probably.
What are those? Sorry, I don't know.
Yeah, so these generalized
Quaternion are
quaternions.
all finite subgroups.
Yeah, so these are the generalized quaternions that it's pin2 is built out of as the realization.
So in X is BG, one of these twisted loop spaces is where projective representations take characters. Is this the same type of twisted loop space?
I don't know what it is, but yeah, but I do want to talk to you about this. I know you have ideas of cool inputs. So the only input that we could think of, right, was this kind of loop space. But yes, I'd love to talk about it.
I was wondering, do you know if you can leverage that theorem to get like an equivalence between, you know, this twisted topological homology and I guess it would be the suspension of twisted equivariance topological André-Quellen?
I don't know. Also very interesting question.
Is it possible to understand cross-symmetry groups as objects in some category of operas using this description? Like you can recover the cross-symmetry group from the operas, right?
Okay. Objects is some category of operands. Yeah, I'm not sure. So do you mean like if the functors between them somehow correspond to maps of operas or something like that?
Yeah. I don't know if this works out.
Yeah, so anyway, I'm not sure. So the only thing that I'm sure of, right, that we have shown is that, I mean, and this is still very specific, right? So we have this specific one, well, these specific ones that we constructed like this, that they correspond to this, you know, so these kind of rings with twisted actions on them. So I don't know if you can even like make a category of those or something.
Okay, let's thank Mona again.